Hello everyone, my name is Choi from Dankook University in South Korea. It is my pleasure to have a chance to present my paper here at USENIX HotStorage 2020. Today I will talk about a new LSM-style garbage collection scheme for ZNS SSD. This is a joint work conducted in cooperation with Dankook University and SK Hynix. This is the outline of my talk. First I will describe what is the NameSpace SSD. Then I will explain the motivation of our study. After that, I will discuss our proposal called LSMG and evaluation results. Finally, I will conclude my talk. There are various types of new SSD, and we call them as next generation SSD. They include open channel SSD, joint namespace SSD, key value SSD, and obtain SSD. The open channel SSD their internals, such as the structure of channels to the host, so that the information can be exploited free for enhanced performance. The joint namespace SSD also explores their internals, but using the well-defined joint namespace interface. The key value SSD supports new interface such as get, put, and scan for key value. Finally, the obtained SSD looks like the traditional SSD, but their media is totally different using PCM instead of NAND flash memory. In this talk, we mainly focus on the ZNS SSD. Okay, now let's talk about what is joint namespace SSD. Unlike the traditional SSD, ZNS SSD divides its address space into multiple zones, as shown in this figure. Divided address space into different zones provides several benefits. The first benefit is that by distributing different workloads into different zones, we can obtain better performance and WAP. Second, it supports better isolation, called the IO determinism among zones. Finally, it can reduce the DRAM usage and overflow visioning area by reducing the FTR functionality in SSDs. However, as you know, if there is a bright side, there is a dark side as well. GNS has two critical issues. One is the sequential write constraint, and the other is the joint garbage collection overhead. Sequential write constraint means that writing in the joint needs to be conducted in sequential manner, like the LSM devise. Therefore, we need to reconsider the conventional I/O scheduling and caching mechanism. The second issue is that in ZNS SSD, host needs to control zone directly, such as zone open, close, reset, and zone garbage collection. In this paper, we concentrate on second issue about how much is the zone garbage collection overhead and how to reduce the zone overhead. To evaluate how much the zone garbage collection overhead is, we make use of ZNS SSD prototype provided by SK Hynix. The information of our ZNS SSD prototype is summarized in table 1. Note that the total size is 1 terabyte and it is divided into 1024 zones, where each zone size is 1 gigabyte. When a zone needs to reclaim, we need to do zone garbage collection. The zone garbage collection is similar to the segment garbage collection in log structure file system. But note that the typical segment size in LFS is 2 MB, while the zone size is 1 GB, 512 times larger. In this situation, we wonder how much is the zone garbage collection overhead. Now, let's think about a simple zone garbage collection algorithm. We call it as the basic GGC. It behaves like the segmented garbage collection in log structure file system and is consists of 5 steps. In step 1, it selects a zone that is a candidate zone for garbage collection. The selection can be made based on various policies such as greedy and cost benefits. In step 2, the algorithm finds out valid blocks in the selected zone using zone bitmap. In step 3, it reads valid blocks from the selected zone. Usually this is done by 4K byte IO size, but it can be done in the larger I/O size if blocks are consecutive, and writes them into a new zone. And finally, it resets the selected zone so that it can be used as a new free zone. This figure shows our first observation. Zone garbage collection was based on basic GGC described in previous slide. The x-axis is the utilization of zone, the candidate zone, while the y-axis is the garbage collection time in seconds. As you can see, when the utilization is 0.4, it takes around 70 seconds. When the utilization is 0.9, it takes around 100 seconds. It's quite a big time. Even though we can hide this overhead using various techniques such as background GC and preemption, this time is still too big. This is because the zone size is much larger than traditional segment for garbage collection. In other words, reducing the utilization of a candidate zone is indispensable in ZNS SSD. Our second motivation is derived from the fact that SSD consists of multiple channels and ways. In addition, a zone in general is mapped into multiple channels or ways in ZNS SSD. Then our idea is how about reading and writing data in a larger I/O size? It can reduce the I/O queuing overhead while obtaining parallelism in SSD. This figure shows our second observation. The elapsed time when access data in a larger I/O size, as we expected in ZNS SSD, we can obtain better performance when we access data in a larger size, since it can reduce the I/O queuing time and it can make use of parallelism in SSD. Hence, our second motivation is that accessing in a larger I/O size is beneficial in ZNS SSD. Based on our two motivations, we design a new zone garbage collection algorithm. We call it as LSM-GC. Our key idea, making the utilization of a candidate zone low and access data in a larger I/O size. The second idea is simple to implement, reading and writing a larger unit, but the coexistence of valid and invalid data makes it difficult to read data in a larger I/O size. Hence, we decide to read not only valid data but also invalid data together in a larger I/O size. Now, the question is how to make the utilization of candidate zone low. One of good solutions for this problem is the hot-cold separation. By the way, the traditional hot-cold separation is not applicable in ZNS SSD, since the zone size is quite big. Assume that there are some range of hot and cold data in SSD. When a management group size is small, we can segregate hot and cold data into separated groups. However, when the group size is big, the hot and cold data co-location in group, making difficult to isolation them. Hence, in this study, we reuse the segment concept for finder grade hot-cold separation. In our LSMGC, data is managed using two units. One is zone and the other is segment. Zone is used for garbage collection, while the segment is used for hot-cold separation. Zone is divided into multiple segments. In this study, zone size is 1 GB and segment size is 2 MB, meaning that a zone divided into 512 segments. In this figure shows the state and transition of each segment in our LSMGC design. When a new data is writing, it is inserted into C0 state. During GGC, C1 data is separated into either C1C or C1H. When a valid data in C0 state is a high utilized segment, it is classified as cold data and inserted into C1C state. Otherwise, it is identified as unknown and inserted into C1H state. This decision is based on our observation that hot and cold data have a spatial locality, meaning that they have a tendency to locate near with adjacent LBAs. This spatial locality is also observed in previous study, such as F2FS, multi-string, key-value range locality paper published in USENIX FS 2020. Finally, the second to survive data is inserted into C2 state. We will show some example in the next slide. This slide shows how our proposed LSMG log structure merge style Jhin garbage collection works. In step 1, LSM scheme selects the candidate zone using greedy or cost-benefit policy like the basic scheme. In step 2, read all data from the candidate zone. Note that the basic scheme reads valid data only, but however, our LSM scheme reads both valid and invalid, which allows to read data always in a larger I/O size. In step 3, LSM scheme identifies the hot or cold segments based on amount of valid data in a segment as discussed in the previous slide. Then in step 4, merge valid data according to hot or cold, and finally the cold data is inserted into C1C zone while others go into the C1H zone. This step looks like the log structure merging algorithm. So we name our scheme as LSMG. Now let's talk about evaluation results. This figure shows comparison between the basic scheme and our proposed LSM scheme. The x-axis, the utilization, y-axis is garbage collection time. In this experiment, we use a write workload that updates data with a uniform pattern. The result shows that LSM scheme can enhance performance by up to 2.3 times with an average of 1.9 times. It's a uniform pattern since your segments are updated with the same probability. The hot-cold separation is not occurred. Hence, the performance gain is obtained by using the larger I/O size in LSM scheme. This slide shows results on the workload that update data with squid pattern. In specs P, is updated data with a 17 and 30 hot-cold ratio, meaning that 30% of data is updated with the probability of 17. In the squid pattern, the hot-cold separation occurred. In this experiment, we set the cold threshold as 0.8, meaning that a segment whose utilization is larger than 0.8 is identified as the cold segment. From this figure, we can observe that our proposition can enhance performance by up to 1.6 times with an average of 1.4 times. In the squid pattern, updates occurred in small range, hence the valid data can locate consecutively, which allows the basic scheme to read data in a larger I/O size. It means that the performance improvements in this figure is mainly obtained from the hot-cold separation. This slide is effective on hot-cold separation. In each graph, the x-axis the zone utilization and y-axis the number of zones that have a relative utilization. In this experiment, we set the initial zone utilization is 0.6. From this result, we can observe that without hot-cold separation, most zones have a 0.5 utilization, and the average utilization is the same as the initial utilization. However, with hot-cold separation, The utilization zone show the bimodal distribution. Some zones have a smaller utilization, while others have larger utilization. This is because our LSM scheme can identify code segments and isolate them into a separate zone. This bimodal distributor allows to select candidate zone that has a smaller utilization, providing better performance. Thus that as the number of garbage collection increases, the bimodal distribution becomes more distinctive. In this study, we make the following three contributions. First, we present our observation that the overhead of drone garbage collection in ZNS SSD is a really big problem. To overcome this problem, we propose a use scheme called LSMG and evaluating its performance using real ZNS SSD prototype. We are currently extending F2FS so that it can run on our prototype and evaluating our scheme on this environment. Thank you for listening. Any question?